In this optimization example, we're going to look at the distance between two things in a two-dimensional plane. Optimization example. Two-dimensional distance. One-dimensional distance is simple. You subtract. In 2 dimensions, it's still pretty simple, but not that straightforward. Not as simple as just subtracting. So let's look at this example. Find the point on the curve y equals the square root of x plus 1 that is closest to the point 4, 0. So find the point on this curve that is closest to the point 4, 0. So we're going to draw a picture of this. Luckily, we're pretty well acquainted with the square root function and what the graph looks like. And so the idea is if I were to graph this curve, it'd be the standard square root function shifted left 1 unit. So it'd basically be like, here's -1 on the x-axis. There's our square root function. And let's say that this is the ordered pair 4, 0. We'd want to find the point on the curve y equals the square root of x plus 1 that's the closest to this point. So what we're looking to do is let's pick an arbitrary point on this curve. We don't know which one it is, so we'll give it a variable name. And let's say that it is at x. We don't know the x value, right? That's what we're trying to figure out, the coordinates. So one of the variables for this ordered pair is going to be x. And then the y value would be y. So we're trying to find the distance between those points and make that as small as possible. So when we say closest to, in this case, that's telling us we want to minimize distance. So we need to find a way to calculate the distance between those 2 points. So let me draw the picture here a little bigger. So we've got this point at 4, 0. We've got this point. It could be anywhere on the curve, so I'm just picking an arbitrary location. We'll call it x, y. And we want the distance between those 2 points. So we're looking for this distance there. Okay, we'll call it capital D. So how can I calculate the distance between those points? And so some of you may be familiar with something that's usually introduced maybe like in an Algebra 2 or intermediate algebra class called the distance formula, but it's really just the Pythagorean theorem. Because what we can do here is we can turn this into a right triangle as such, and we know the distances for the legs. So what I'm going to do is move this ordered pair over so I have some more room to write. So this is 4, 0. So this horizontal distance between these 2 points is literally the same thing as the difference between their x coordinates. So the x coordinate here is 4, the x coordinate here is bigger, and it's x. So this leg length is going to be x minus 4. This x value minus that x value. The vertical distance between these would be measured by subtracting the y values. So I'll take my top y value, y, and subtract my lower y value, 0, and get y minus 0, which is equal to just y. And now from this picture, because I have 3 sides of a right triangle, I can come up with my function, my distance function, which we're trying to minimize. We're trying to minimize distance. So I need a distance function, which is d equals, and by the Pythagorean theorem, it's going to be the square root of this leg squared plus that leg squared. Okay, so that's my distance function, and I want to minimize it. I can't do that yet because I have two variables here. Now, this is a bit different than other examples we've done because this is not really like a geometric relationship between x and y in the usual sense. So if we come back to what y is literally, this is what we know, y is literally defined to be the square root of x plus 1. So I can substitute that in for y, and I can substitute that in for y here also. And so by doing that, my distance function now, in terms of one variable, turns into the square root of x minus 4 squared plus the square root of x plus 1 quantity squared, because y is the same thing as the square root of x plus 1. Okay, very good. So we've gotten this far. We have our function that we want to minimize in terms of a single variable. We have to find the critical numbers. We have to look at the derivative, all that kind of stuff. But let's clean up this mess a bit first. And you know from your basic algebra, you can't cancel this big square root with each of those squares, unfortunately, because we're adding. You'd have to be able to add these together before you could apply that square root. So we're stuck with the square root. But squaring x minus 4 gives us x squared minus 8x plus 16. And luckily here, squaring this square root just gives us x plus 1. So now I've got x squared minus 7x plus 17 all under my square root. And that's my distance function, okay? So let me recopy my distance function. I'm kind of running out of space. So d equals the square root of x squared minus 7x plus 17. Now I can get rid of all of this. So that's my distance function. And I need to differentiate my function so I can find the critical numbers, etc. All right, so d is all of this to the 1/2 power. So when I differentiate that, I'm going to get a 1/2, so I'll get 1 over 2. And I'll have this whole thing to the negative 1/2 power, which just means the square root of all of that on the bottom. Okay, so that's the derivative of a square root. 1 over 2 of the square roots. But then I have to apply the chain rule and multiply by the derivative of what's inside, which happens to be 2x minus 7. So this is my derivative function. And I need to find the critical numbers now. So I need to know where it equals 0. In other words, where does the numerator equal 0? And I need to know where the denominator equals 0. And I'll solve those to find my critical numbers. Where the derivative is 0, where the derivative does not exist. So this one's simple enough. X equals 7/2. Okay? Something else to notice here is that the x values here, x has to be greater than or equal to -1. So we're not concerned with x values less than -1. And luckily 7/2 lies in that region. It's 3.5, right? Just to the left of that 4. Now to solve this, I can't use standard factoring because I can't multiply two numbers that add to give me -7. So I'm going to use the quadratic formula. So I've got positive 7 minus the square root of 49 minus 4 times 17 all over 2 times 1. And luckily here, the square root of 49 minus 68 is negative. So these x values are imaginary. That means we don't get any critical numbers out of this. So this is our only critical number, x equals 7/2. Now we can create our chart to plot the derivative versus the distance function and find out if we can minimize this distance function. So I'll set up my x row, my d prime row, and my d row. And I'll put my critical number 7/2 right here. Over here, I'll have x values bigger than -1, but less than 7/2. And over here, I'll have x values bigger than 7/2. We already know that when x is 7/2, the numerator was 0, so d prime is 0. And if d prime is 0, then d has a horizontal tangent line. Now if I look at x values to the left of 7/2 and plug them in here, that's going to be negative, and 2 times the square root is always positive. So negative divided by positive is negative. On the opposite side, if I look at numbers bigger than 7/2 and plug those in, I'll get positive on top over positive on bottom, which is positive. So we have this square root function. By the way, don't confuse this. This distance function is not the same thing as this graph. This is the graph of the square root of x plus 1, not the graph of the square root of x squared minus 7x plus 17. So this particular distance function decreases, this distance decreases for these x values, and the distance increases for the x values bigger than 7/2. So if the function is decreasing, hits this horizontal tangent line, and then starts increasing, then this has to be the absolute minimum, okay, at x equals 7/2. The question asks us to find the point, right? I have to find the point. Well, I know that for the point, I need my x value. It's an ordered pair, so I need my x and I need my y. So I know that x is 7/2, but I also need to know y. And I know that y is the square root of x plus 1. So I can say that y is the square root of 7/2 plus 1, which is the square root of 9/2. And if we simplify a little bit, we get 3 over the square root of 2. So the point that we're searching for here is the point where x is 7/2 and the y is 3 over the square root of 2. So that's the point on this curve, which happens to be over here, right? 7/2 is 3.5, so that's the x value. This point right here is the one we're looking for that we just found. This distance here is the shortest distance between any point on that curve and this point, 4, 0. Now, the question could go further and say, what is the distance between this point and this point? And that would be simple to figure out, because we could take the x value that we found that minimizes that distance, and we could plug it back into our distance function to calculate the actual distance between this point and 4, 0. But anyway, that's another example of optimization, trying to expose you to as many concepts as possible involving geometry, distance, whatever it may be.